The question we want to start off class with today, we've got a system of 3 pulleys, two 10-kilogram masses. Let's call this one number 1, number 2, and number 3. We want to find the acceleration of this system. What's the difference between maybe this question and a question that we've done that looks a lot like this question? Yep. Yeah, I've got not a force of friction given to us here. We've got a coefficient of friction. Let's see what you can do with that over the next 2 minutes, let's say, and then we'll take a look at it as a group. All right, let's have a look at it. One of the things that we probably should do with this one, it's not critical, but not a bad idea, is straighten it out, right? So if we do that, we got a 10-kilogram object like this. We have another 10-kilogram object like this. We have a 20-kilogram object like this. We have a force of gravity acting on object number 1. I'll call it FG1. It's going to be equal to 10 times 9.81. We have another force of gravity acting this way. This is bigger, so I'm going to draw it longer, twice as long, in fact. And I'm going to call this FG2. We do have one more force acting. What is that force? Friction. And it's going to act between the 10-kilogram object and the surface right here. Now, it doesn't really matter where I draw it, but I'll draw it with the 10-kilogram object. It's going to act which way, left or right? This system is going to move to the right, which means that the force of friction is going to oppose the motion and act to the left. I don't know what its value is right now, but I can find its value just like I can find the value of the force of gravity on 1 and 2. There we go. There's my free body diagram. By the way, there is a normal force and gravity acting on this one as well, but they cancel each other out, so you can either cross them off or just avoid drawing them. All right, let's do the next step here. F net is equal to the sum of the forces, Fg1 plus Fkf, the force of kinetic friction on the middle object, and Fg2 is our next one here. F net is m times a equals Fg1 plus Fkf plus Fg2. And then we start subbing in some numbers here. The mass we use is what? 10, 10, or 20, or some kind of combination of those. 40, it's the combination of those, right? The acceleration is what we're looking for here. Fg1 is 10 times 9.81 plus Fkf, the force of kinetic friction. How do I find that? Is it 0.30? No. Yeah. I got to times that by the normal force, right? 0.30 times the normal force would be 10 times 9.81 here. We're on a flat horizontal surface with no upward or downward acceleration, at least on that object, no upward or downward acceleration. And then we're going to add to that the force of gravity on the third object, 20 times 9.81. Now, where's the mistake or mistakes here? What have I left out or done wrong here? Nick? Yeah, I need a negative over here. Now, I didn't really leave space to put it beside the 9.81. It's okay to put the negative in front of the whole thing. It doesn't really matter where I put it as long as it goes with that term, right? Good? Anything else? Anything else here, Kessler? Friction is going to be negative as well because it's acting to the left in that system as well. Again, it doesn't matter whether I put it with the 9.81 or in front of the whole thing, as long as I put it with that term. That force is to the left, so it's going to be negative. Now, some of you may have made that force positive and that force positive. That would be okay if you did what? If you made this one negative, right? As long as this one is opposite in sign to Fg1 and Fkf, then you're good to go there. All right, 40 times the acceleration equals negative 98.1. Subtract 0.3 times 10 times 9.81 is 29.43, I believe. Plus 20 times 9.81 is 196.2. So we've got 40 times the acceleration. $68.67 on the right-hand side. And then we divide that by 40, and what are we going to get here? Around 1.5-ish, 1.56. What is it? 1.7? Meters per second squared. What are the other set of units that I can use for acceleration? I barely ever use them, but there is something else that I can do here besides meters per second squared, right? Yep. Newtons per kilogram works as well. Good. You guys are good there? I can promise you that the quiz that you're going to have tomorrow on this stuff will be no harder than this. Okay, I promise you that. I don't even know, to be honest, if I have a coefficient of friction in there. I don't remember. The quiz has been made up for a little while, and I don't remember whether I put that in there or not. But if it is, look, you know how to deal with it. Okay, if it isn't, then the question is going to be even easier. But I can promise you that the question is not going to be any harder than the question we just did. All right, make sure you're ready for that. If you need help with it before then come and see me at lunchtime or scheduled help today, and we can take a look at that. All right. On Friday, we went a step further and did something that I think is a little bit more challenging, maybe the most challenging thing that we do in this unit, actually. We looked at what we call incline planes, which is a fancy word for a hill. We call them incline planes. Why do we call them incline planes? I don't know. Maybe we want to sound really, really smart. If we're analyzing hills, that doesn't sound like it's too hard, too crazy, eh? If we're analyzing incline planes, I don't know. Maybe it makes us feel a little bit smarter or something. I don't know. Anyways, that's what we call them, is incline planes. Now, in this particular incline plane, we're going to have an angle of 30 degrees here. We're also going to have a mass on that hill of 10 kilograms. There is no friction. There's no other forces acting other than what you see here right now. It's the hill itself. All right, let's draw a free body diagram for what we do have, the forces that we do have. Okay, the first thing we have is going to be what? Gravity. Gravity acts straight down toward the center of the Earth. It does not act perpendicular to the surface unless the surface is horizontal. It acts toward the center of the Earth, which is straight downwards. We're going to label that the force of gravity, or m times g. We also have a normal force. Which way does a normal force act? 90 degrees to the surface. Now I can draw that normal force up here, but I don't want to do that this time. Okay, we're allowed to draw it wherever we want, so technically that's not wrong, but it's not going to be overly helpful if I draw it up there. So I'm going to choose to draw it down here. What's really important about this normal force when we draw it? What do we have to be really, really conscious of when we're drawing this normal force? Yeah, go ahead. Yes, okay. A, that it's drawn front to back. So we've got the normal force drawn front to back to the force of gravity, absolutely. B, that it's drawn at 90 degrees to the surface. And C, that we've drawn it roughly the right length, such that this line that we're calling F parallel, that's the sum of those two vectors, the combined normal force and force of gravity. That force needs to be drawn from start to finish, and it needs to be drawn parallel. So if you have it drawn like this, yeah, it looks good, right? Well, tell me what's wrong with this. F parallel is not parallel. Okay, that doesn't work. Okay, this force right here is not going to pull this object down the hill. The direction that it moves is down the hill. So there has to be a force that acts down the hill. And that down the hill force is F parallel that comes as a result of adding together the normal force and the force of gravity. This is F parallel. I'm drawing it in two places. There's only one of them, but I'm drawing it in two places here. Right, Kessler? And that F parallel must be drawn at 90 degrees to the normal force. Got it? Why does it have to be 90 degrees to the normal force? Well, because the surface is 90 degrees to the normal force. That's how we define the normal force. And F parallel is parallel to the surface. Now, what do we know about this angle right here? It's going to be the same as this angle right here. So if this is 30, this has got to be 90 right here. This is 30 and this is 90, this has got to be 60. And if this is 60, then this one's got to be 30. And that's always going to be the case. Okay, whatever the angle is down here of the hill, then the angle is going to be the same up here within our triangle, right angle triangle. All right. Now we've done the hard part. Now it's a matter of doing the analysis here. Now it's a matter of figuring out maybe what F parallel is, and maybe if we need to, what the normal force is. We can find F parallel by saying sine 30 degrees. Sine 30 degrees is equal to opposite. The opposite side of that triangle is F parallel over the hypotenuse. And the hypotenuse is the force of gravity, m times g. So we'd say in this case, F parallel is equal to m times g, 10 times 9.81, times sine 30 degrees, which is 49.05 newtons. So the force that pulls it down the hill is a combined force. It's a combined force of normal force and gravity, and it gives us a combined value of 49.05 newtons. When you put something on a hill and it accelerates down the hill, does it accelerate down the hill at an acceleration greater than 9.81 or less than 9.81? Less. Yeah. Like it doesn't accelerate down the hill as quickly as it would if you just dropped it, right? Why? Well, look at this. The force of gravity would be 98 newtons straight down. If you drop something straight down, it accelerates with a force of 98 newtons. But if we let it go down the hill, it accelerates down the hill with a force of 49 newtons, half the force, right? So it's going to end up experiencing half the acceleration. All right? Well, now what would we do next? Well, the next part of this is the same as we've done a million times with all of our other force questions. The net force is equal to the sum of the forces. In this case, all we'd have would be F parallel. If we had friction, we'd add that in as well. The net force is 10 times the acceleration. F parallel is 49.05. Usually I make the force that's down the hill negative. Everybody know why I left it as positive this time? No, not so much absolute values. No, we're not dealing with absolute values here. We do have to pay attention to direction, but listen, if you only have one force acting, you might as well make it positive, right? Right, if we had another force acting up this way, then I probably would have made that 49.05 negative. And it's certainly not wrong to make it negative now. But if I've only got the one force acting, let's just drop the negative. I end up getting A is equal to 4.9 meters per second squared. And because I define down the hill as positive, that's a positive acceleration. Yep. Okay, good question. Instead of writing negative or positive, can you write the word down or up the hill? I mean, technically, I should have said this, right? Down the hill is positive. But can you write down or up with this? Yes, you can. But be careful. If there happened to be a force of friction here, there's not in this question, but let's say there was for a second, and friction was, I don't know, 10 newtons. You wouldn't want to say 49.05 down and plus 10 newtons up the hill. Because how do you do the math with that, right? Yeah. So let's make one of those negative in that case. It's okay. Like technically, it's okay to write the words in instead of the signs, but mathematically, it's not fun. Oh, yeah. At the end, absolutely. At the end, it's absolutely fine to do that. It's just you probably don't want to do that through the question. That's all. Especially if you have more than one force acting. All right. You guys had a couple questions for homework on page 179. I suspect that we had a little bit of an issue with one or both of these questions. We went through the example relatively quickly in class on Friday, and it was towards the end of class. So if you struggled with this a little bit, that's okay. I get that. Is there anything from these two questions that you want to go over, one or both of them? Number two? Okay. Let's go over number two. Then we're going to do another example anyway, so maybe that'll help us with number one if anybody had trouble with that. Number two says a 55 kilogram skier is accelerating down a 35-degree slope. Who would have made the slope 35 degrees, huh? Why would they made it 30 degrees? It's trying to make life difficult for us. Here's the hill. We got an angle of 35 degrees here. And we got a skier here. Looks kind of more like a toboggan, I guess. Stand-up toboggan. But we want to find the force of friction. We have an acceleration of 4.41 meters per second squared. Listen, is the force of friction going to be up the hill or down the hill? Sorry, is the acceleration going to be up the hill or down the hill? Down the hill, right? I'm going to make it negative because friction is going to oppose that, so friction is going to act up the hill. Let's draw in friction right now. Actually, let's wait to draw in friction. It doesn't really matter when I do it, but I'm gonna choose to wait. I got a force of gravity acting down, it's m times g. I've got a normal force acting perpendicular to that, like this, Fn. Notice I've drawn it such that the combined force there, F parallel, is parallel to the hill. I don't know what the value of F parallel is. I'm going to have to find that, right? Right, Zach? The force of friction acts this way. I'm going to draw it shorter than F parallel because it accelerates down the hill, meaning the downward force, F parallel, has to be bigger than friction. That's what we want to find, right? We got to find F parallel first, but ultimately we want to find FF. Okay, let's get F parallel right now. Let's say sine, we know this is 35 degrees, right? Sine 35 degrees is equal to opposite F parallel over the hypotenuse. So F parallel is equal to mg sine theta, 55 times 9.81 times sine 35 degrees. Who's got a value for that? 309. Okay, so there we go. There's my F parallel. Let's label that in right here. 309.473 newtons. We still don't know what FF is. That's okay. That's what we're going to find in just a moment here. All right, now let's say what? What comes next? Yep. Right. Let's say F net is equal to the sum of the forces. We're going to say the sum of the forces is F parallel plus the force of friction. Let's replace F net with m times a. Mass is 55. Acceleration is negative 4.41. Negative because it's down the hill. F parallel will be negative 309.473 because it's down the hill. Plus the force of friction. There we go. Solving for a different variable than we usually solve for here, that doesn't matter. We set it up exactly the same way, right? 55 times negative 4.41 is going to give me negative 200 to something. When we add 309, we're going to get 66.9. Positive 66.9. Which means since we defined down the hill as negative, means that positive value means up the hill, right? You could write in the word up the hill, or you could just leave it as positive if we defined down the hill as negative. Good. How many people got that? Okay, how many people feel a little bit more comfortable with that question now than they did at this point when they were trying it on the weekend? Okay. All right, let's have a look at this one. Loonie with a mass of 7 grams is at rest on an incline of 25 degrees. Calculate the force of static friction acting on the loonie. All right, what comes first here? Let's draw the free body diagram. Listen, it doesn't matter what we're asked for. Let's draw the free body diagram. On the loonie, we have gravity acting down, straight down. We have a normal force acting perpendicular to the surface. Tell me when to stop drawing the normal force, okay? Tell me when to stop. Stop right there. I stop right there because that makes F parallel to the hill. Now remember, there's not two F parallels. I'm drawing it in two places, but there's not two of them. There's only one of them. I'm just drawing the same force in two places. Okay, this is more useful when I go to actually calculate the net force. This one's more useful in finding the value of F parallel. Force of static friction acting on the loonie. Which way does static friction act? Backwards, up the hill? Tell me when to stop drawing the force of friction. I'm running out of space here. Tell me when to stop drawing. Let's try that again, okay? Tell me when to stop drawing the force of friction. Right there? That looks about the same length as F parallel. Is it supposed to be? Supposed to be the same length, or supposed to be a little bit longer, a little bit shorter? If it's bigger, if the force up the hill is bigger than the force down the hill, what's going to happen to this object? It's going to go up the hill. Static friction can't be bigger, right? Maximum could be bigger, but static friction can't be bigger. Is it going to be smaller? Well, if it was smaller, then it would go down the hill. If this thing is going to be at rest on the incline, what do we know about F parallel and FSF? They're going to be the same, right? Let's get F parallel here. We know that this is 25 degrees. This is 90 degrees. Let's say sine 25 degrees is equal to opposite over hypotenuse. 0.007 kilograms times 9.81 times sine 20 degrees. Sorry, that should be 25 degrees, right? It says 25 up here. Can't read my own writing, though. What do we get there? 0.2902. Thank you. All right, now I could, because I know that F parallel and FSF have to be the same number, I could just set them equal to each other. But listen, if you didn't recognize that, if you didn't catch the fact that they should be equal to each other, that's okay, actually. You can get away with that. You could just say at this point, F net is equal to the sum of the forces, F parallel plus FSFF. FSF. Mass is 0.07. What's the acceleration here if it's at rest? 0. So the net force would be 0. F parallel is 0.2902, probably make it negative. FSF is, well, I'll rearrange that, and it becomes positive 0.2902 newtons, or 0.29 newtons. You don't need to go through this. Okay, if you look at this and say, oh, look, I know that FSF is the same as F parallel, then I can just say FSF is 0.29 newtons, right? But if you don't catch that, then you can still go through the same processes we've run through, just making sure that you recognize that acceleration is 0. All right? Okay, let's have a look at these two questions, please, on page 175. Let's have a look at question number 2. Here's our hill. We don't know the angle, actually, this time, theta. It says the loonie of mass 7 grams. They really like these loonies here. 7 grams, 0.0070 kilograms. It's placed on a rough book. Calculate the maximum angle at which the book can be inclined so that the loonie begins to slide. So the book really has nothing to do with it here, right? The book is just the surface that it's on, but the book is going to be the same angle as the hill, so the book is really irrelevant. All right, what do we got here? Well, we have force of gravity acting down on it. Call that Fg, or m times g. We got a normal force acting this way. Call that Fn. We got F parallel acting parallel to the surface here, like this. This is going to be theta. We don't know what the value is there. We know that that's going to be 90 degrees. We know that we have a force of friction, a force of static friction acting opposite to that. Now, it doesn't actually say this, but it should. It says a force of static friction of magnitude 4.4 times 10 to the negative 2 newtons acts on the coin. What it should say is this is the maximum force that can act on the coin, or the force that acts on the coin when it begins to start moving, right? So we're going to assume that FSF max, even though it doesn't actually say that, is 4.4 times 10 to the negative 2 newtons. And then what? Now let's say F net is equal to the sum of the forces. We're going to say F parallel plus FSF max. If this is FSF max, the force of friction that is acting just before it begins moving, then what's the acceleration? 0. So we're going to say m times a is 0. F parallel is, we don't know, FSF max. We do know what that is. It's 4.40 times 10 to the negative 2 newtons. So we know that F parallel will be equal to 4.40 times 10 to the negative 2 newtons. It's not what we're looking for, though. Where do we go from this? Listen, I've said this a million times, though, right? If you're not sure where to go with something, look, try something. We just tried something. We didn't get an answer. Let's keep going. Let's try something else. Okay, so what do you want to do? Yeah, let's do the opposite of what we've been doing, right? Instead of saying sine whatever theta is equal to opposite over hypotenuse, solving for opposite, let's say we know opposite, use the same equation, sine theta is equal to opposite over the hypotenuse, which is m times g, 0.007 times 9.81. So let's say sine theta is equal to 4.4 times 10 to the negative 2. What's that number on the bottom there, Kelsey? Do you have that? 0.0686. 6867. So, and now we're going to say theta is equal to the inverse sine, second function sine of those numbers here. So let's say second function sine 4.4 over 0.06, and we should end up, I think, with 39.8 degrees there. Anybody get that? You might do it differently and get the right answer, that is. More or less like this. Listen, could we have avoided writing all this stuff down? Sure, we could have if you had spotted that, oh, wait, the maximum force of static friction has to be equal to the force parallel, the force of the hill acting down, then we could have avoided that. But if you didn't spot that, listen, that's okay. We can figure that out like we just did. All right? All right, let's do one more example, and then I think that'll be it for me today. Not for you, but for me. 50-kilogram toboggan is on a snowy hill. If the hill forms an angle of at least 20 degrees at the horizontal, the toboggan just begins to slide down the hill. Calculate the coefficient of static friction for the toboggan on the snow. Boy, I don't know about you, but when I look at this question, or at least if I was looking at this question for the first time, I'd be like, that's different. Solve for the coefficient of static friction. We haven't done that before. How do I do this? I don't know exactly. So let's just try something. What do you know to try here? Get F parallel. Like you know how to do that, right? So do it. We've got force of gravity acting down. We've got the normal force acting perpendicular. We've got F parallel acting parallel to the surface. Make that 90 degrees. We'll make this 20 degrees. We've also got friction acting backwards, right? Friction's acting backwards this way. Well, I don't think that's going to help me right away. Eventually it's going to, but. All right, let's get F parallel. Let's see what we can do there. Let's say sine 20 degrees is equal to opposite, which is F parallel, over the hypotenuse, which is m times g. So F parallel becomes equal to, what do we got here? 50 times 9.81 times sine 20 degrees. Man, I wish I just used 30 degrees. Make life easier for all of us here. Anybody have that? 184.536. Okay, thank you. Now, if it just begins to move, what do you know about the force of friction here? It would be the max force of static friction, right? If this is the force that's required to get it moving, that's the same as the max force of static friction. If you don't recognize that, listen, that's okay. Just say F net is equal to the sum of the forces. What would the net force be? Mass times A is 0. So you're going to find that FSF max ends up being equal to 184.536. Remember those questions we were doing with friction earlier in the unit? The force that was just required to get it moving was equal to the max force of static friction. No different here. Yep. 167. Oh, Bruce. Shame. What is it? 167.76. Thank you. All right, any ideas for now? Solve for the coefficient, somebody said? Oh, find the normal force. Oh, yeah, look. I can't even say it. FSF max, we know is equal to mu times the normal force, right? We want to find mu. So any ideas how I'm going to get the normal force here? I need it, right? I've got this value, 184, but I need Fn. Oh, come on. Somebody who hasn't answered a question yet today, show me what you're made of here. How are we going to find the normal force? Kelly? Okay, you can do that. That's not what I was thinking, but that would work. We have the force of gravity. We have side A, F parallel. We could use the Pythagorean theorem, absolutely. Anybody else thinking that? Okay, the thing that I was thinking was, yeah, I was thinking cosine 20 is equal to adjacent over hypotenuse. Does it really matter which way we do it? No, not really. The only thing, the one downside to the Pythagorean theorem is if I made a mistake with F parallel, that mistake's going to carry through if I'm using the Pythagorean theorem. Fn is equal to mg, which is 50 times 9.81 times cosine 20 degrees. And what does that work out to be? Bruce, you got one for me? 460.919. Are you sure? Look at that. Now we got this force as well. Now it's easy to find mu, right? It's FSF max, which is 184.536, divided by the normal force, which is 460.919. And that's going to give me a value of about 0.4-ish or something like that. 0.36. And there are no units because it's newtons over newtons, and the units end up canceling. Thank you, Mallory. We do have a bit of a typo here. This should have been 167.76. This should have been 167.76. But miraculously, we end up with the same answer here of 0.36. Boy, oh boy, oh boy. Here's another couple of questions for you on page 186. See what you can do with that one. Remember, don't be afraid to try. You're not sure where to go with something? Just think about what you know and do something that's valid. And it's amazing how it just falls into place.